So, let us look at the tetragonal and how the tetragonal representation takes place. This is a bit of a change from the triclinic, monoclinic and the orthorhombic. In case of the triclinic, of course, we do not have to worry about A, B or C, because A is not equal to B, not equal to C. So, we can take any of those three crystallographic directions, and in fact, there is no question of any rotation axis associated with that, and therefore, as a consequence, we need not have to worry about the direction in which we fix the axes, because there are no axes in case of triclinic. In the case of the monoclinic system, we had the choice, and the choice is either A, B or C, depending upon what two angles we would like to take as 90 degrees, and technically and from convention it is always the B axis which is taken as the unique axis. So, the y direction is the direction in which the two-fold axis exists in case of the monoclinic system, and therefore, we normally refer to this as the unique axis, the B axis. It may be possible to have a different setting in a monoclinic system where we can also have either A or C, in which case we have to mention the uniqueness associated with the two-fold axis. When we come to the orthorhombic system, we have no choice because A, B and C all three are two-fold axes, and so the nomenclature is that first when we say a point group like 2, 2, 2, the direction is now along A, along B and along C, the three directions. So, as far as up to the point of orthorhombicity is concerned, the order is A, B and C. When we come to the tetragonal system, the order changes, and this is something which is not mentioned in any textbook, and people forget about it, or in fact people are ignorant of it. And that is where I thought I should mention that the four-fold axis associated with the tetragonal system always comes in the beginning. So, when you say a point group symmetry, when you see a point group symmetry starting with a 4 or any of the proper and improper inversion axis associated with the four-fold axis, like 4 by m or 4 bar or 4 1, 4 2, 4 3, then it means that we have a tetragonal system. So, tetragonal system is characterized in terms of the first number associated with the z direction. We always have this along the z direction. The twofold is then, since we have 4 2 2 as a possible combination of three axes. See, in tetragonal we can have only one four-fold axis alone, and that itself satisfies the condition required for a tetragonal symmetry. That means A not equal to A equals B not equal to C, alpha beta gamma 90 degrees. So, that is a single axis operation. We can also have the three axis operation as per the rules of the Euler's theorem. Then we have something like 4 2 2, which we have already seen in the previous class, and in this case we have a proper improper axis which is 4 mm. So, this combination is also allowed. And then the second twofold therefore, or the mirror symmetry represents a proper and or of inversion along the x direction. So, the fourfold is along the z direction, the next twofold or any associated twofold with mirror, inversion and so on is along the x direction. And then that leaves us with the third twofold axis, which is again proper or inversion, and that proper or improper and or inversion, and that goes into the direction which is 1 1 0 in the crystallographic nomenclature. What we mean by this 1 1 0 is whenever we have a nomenclature like this in square brackets, it means that it is a direction in the crystallographic point of view. Suppose we have a crystal structure with A, B and C as the directions, x, y, z are the directions to which A, B and C will now coincide, in which case we will say that 1 1 0 means 1 unit along the x direction, 1 unit along the y direction and 0 along this. So, this represents therefore a crystallographic direction So, this is a vector which is pointing out in a direction which is 1 1 0, characterized by 1 1 0. Just to complete the discussion on the nomenclatures, if you have open square brackets, it is a crystallographic direction, and if you have them in normal brackets, it represents crystallographic plane or planes, the family of planes in that particular orientation. We will be discussing this in more detail when we go over to the space group nomenclature and beyond, and particularly when we discuss the scattering coming from X-ray diffraction. I think in that context we will postpone the discussion on the nomenclatures here. Just to remember, you should remember, and when we discuss it we will recollect that PQR in brackets, square brackets, represents crystallographic direction. PQR in brackets, normal brackets, represents a crystal plane, and if you have this flower bracket, it actually talks about family of planes. In fact, it is coming very often in higher symmetry point groups, and we will discuss this again with respect to the crystal and the X-ray diffraction conditions which follow as a consequence of it. So, just remember that these are the nomenclatures you will find in textbooks, and one has to be very cautious in looking at these brackets carefully, and then the meaning associated with those brackets when someone writes a technical paper in the area. So, the tetragonal system therefore can be 4 mm, which is essentially a proper improper axis, and in this particular case down here it is 4 by m 2 by m 2 by m. In fact, 4 by m 2 by m 2 by m can also be written as 4 by m mm, and that is the shorter form of this. Essentially it means that we have a combination of a proper and an improper axis associated with each direction. So, for this 4 by m 2 by m 2 by m means that there is a 4 by m symmetry associated with the z direction, and then a 2 by m symmetry associated with the x direction, and a 2 by m symmetry associated with the direction 1 1 0. So, this is how a tetragonal point group representation comes up. Having seen this, let us go further into the trigonal system. So, we see now that a similar nomenclature is utilized in the case of trigonal symmetry as well. So, the threefold axis, proper inversion along the z direction. So, now the threefold takes the z direction in the representation, and as we discussed in the case of the tetragonal symmetry, the threefold will also be along the z direction, and it can stand alone or it can be with a combination of two other symmetries like 3 2 2 for example. So, here is an example where we see that there is a stand-alone threefold, stand-alone 3 bar, and then we have here 3 m. Essentially it means that it is a proper and an improper combination. So, obviously the third one will be also an improper axis, which is not represented generally. And 3 bar 2 m now represents the presence of 3 bar and then a 2 by m, which is proper and improper simultaneously, and then the last one, which is 3 2. I am just writing a question mark here and saying that it is a proper improper or proper by improper or improper by proper, whatever that is. I want you to find out what could be the symmetry in the third direction given this nomenclature. Similarly, in the case of 3 2, it is probably easier because I have already written proper. So, that will tell us the issue associated with 3 2 2. So, basically what we are now representing are the 5 possible point group symmetries that can be associated with a trigonal system, and the z direction is the threefold axis. The twofold axis is again along the x direction, and the twofold which is proper and of inversion or whatever, is just notice that there is a change between the tetragonal and the trigonal system. In the tetragonal system, in the trigonal system it is 1 1 bar 0. In the tetragonal system it is 1 1. Let me point it out with a laser. It is 1 1 bar 0. In the case of the tetragonal system it was 1 1 0. So, having seen the trigonal and the tetragonal, which are represented in the corresponding threefold direction and the fourfold, it is obvious that the hexagonal system will again have a z axis representation of the sixfold symmetry. Remember, when we did the point group symmetries which can exist just along one axis, we discussed the possibility of 2, 3, 4 and 6, and the 2 corresponds to a monoclinic system, 3 corresponds to a trigonal system, 4 corresponds to a tetragonal system, and 6 corresponds to the hexagonal system, and therefore, we have 6 and 6 bar which are indicated here, and along with that goes the 6 by m symmetry. So, these are standalone single rotation axis symmetries. But we can also have the combinations like 6 to 2 for example, which means that the two-fold axis now again along x and the two-fold proper or inversion again along 1 1 bar 0. So, there is no much difference in the direction aspect, except that the symmetry is now controlled by the presence of the six-fold axis compared to the trigonal system where it was controlled by a three-fold axis. In fact, there is not much of a difference between the trigonal and the hexagonal. We do not have enough time to go into the discussion of how the systems can be, for example, hexagonal can be also viewed as a rhombohedral system. Maybe in one of the TA classes this can be discussed, the hexagonal to rhombohedral system, and then how the rhombohedral system develops, and both of them can be converted one to the other. This is something which maybe can be done in one of these classes, but I generally feel that it is not immediately required for the continuation of this course. So, we will assume that hexagonal and rhombohedral are convertible to one to other. I just want to give you a take home lesson at this point. Find out the conditions of the rhombohedral system. That means what are the relationships between A, B, C and alpha, beta, gamma, and then you see that there could be a relation between the rhombohedral and the hexagonal system. So, these 7 point groups now belong to the sixfold hexagonal symmetry, and these point groups therefore represent the standalone symmetry axis and then the combination of 6 and 2 and 2. And the arrangement of the axes are shown here. So, depending upon the sixfold symmetry, we will develop 6 two-fold orientations on either side of the sixfold symmetry direction, which is the z axis. So, having seen this system, we now go to the system which is the most simple system, but most complicated to understand, and that happens to be the cubic system. The reason why it becomes a little more complicated to understand is because that of the fact that the association of the rotation axis is not in principle with an origin and then the x direction, y direction, z direction. As you can see here that in this particular case you have a 2 3 3 represented in this particular diagram, which essentially outlines a tetrahedral type of an arrangement, and the cubic, which is 4 3 2, it actually represents an octahedral type of an arrangement. So, here what we do is we refer to the center of the cube rather than one of the cube edges. So, the symmetry information, the symmetry axis information will go with respect to the center here, and as a result we have a threefold rotation along the diagonals, and these 3 diagonals are shown here with a threefold rotation marked on them. And then we will also have the twofold axis or the fourfold axis in this particular case, which is along the direction along the twofold or fourfold, that is the symmetry along the x direction, and then there is a threefold along the 1 1 1 direction. So, what you see here is that the representation of the space group therefore, which is now shown in the stereographic projection. So, the stereographic projection therefore is with respect to the center of the cube, and effectively you take this cube and put it inside this sphere and mark these up and down points as per the definition of the stereographic projection as open and closed circles. Then you will get the entire symmetry that is possible to be marked out on the stereographic projection, and that is why the stereographic projection looks a little not so very easy to understand than the previous case, but if you look and compare this diagram with this diagram, you will start seeing the intersection points which are appearing here as different kinds of rotation axes. So, in a typical cubic system, we can have a two-fold along the x direction or a four-fold along the x direction. We will also have a compulsory three-fold along the diagonal. The diagonal now is 1 1 1. The presence of the compulsory threefold makes it unique, associated with as a unique symmetry that is associated with a cubic system. So, when we describe these possible 1 2 3 4 5 point groups with the cubic system, we have to consider the fact that we have the center now is associated with the center of the cube. So, the representation here is 2 3, of course, obviously the third axis is also three-fold axis, which is not necessarily written here. So, suppose you come across a space group which is 3 2, and then there is a come across a point group which is 3 2 and a corresponding point group 2 3, it is now easily discernible. So, if the number the axis number starts with 3 in the beginning, that means it is a three-fold axis which is along the z direction. So, it belongs to the trigonal system. In this particular case, the two-fold is with respect to the x axis. So, the first one is again in the cubic system, the first representation is along the x axis or the a direction, because a, b and c are same in a cubic system. We can call it as a rectangular system because alpha, beta, gamma are also 90 degrees. So, we can use x and a interchangeably here. So, the two-fold symmetry or the four-fold symmetry in this particular case, the different point group symmetry, in both these cases we use that as the symmetry identifier along the x direction. Now, the fact that we get a two-fold and a four-fold along the x direction does not just stop there, because we have the following three-fold symmetry here and a three-fold symmetry here. Once again, you see there is a three-fold symmetry and a two-fold symmetry which comes along the 1 1 1 direction. And this is the way in which we now identify the cubic point group, because if you have a compulsory threefold along in the second position throughout all the point group symmetries, the presence of the threefold, or of course the related inversion center or the related mirror symmetry, as in this particular case this is a 3 bar, 3 and 3 bar are both associated with a single direction axis. So, we have therefore the presence of the threefold as a very common and unique representation, and that will come always in the second position in the point group symmetry, and we will see that when we look at the associated space groups, which will be a very large number in the case of the cubic system, because cubic system can support different kinds of lattices. Cubic system will support a primitive lattice, it will support a face centered lattice, it will also support an eye centered lattice, and as a consequence we get a large number of possible lattice symmetries that can be associated with these point groups. So, to cut the long story short, cubic is the most symmetric system one can think of. The distribution of the symmetry elements in the cubic system looks too very complicated, but it is fairly straightforward in the sense that it is either a two-fold or a four-fold axis along the x direction. The three-fold compulsorily is along the 1 1 1 direction, and then the third direction could have either a two-fold or a four-fold, as we can see here. It could also be, of course, a combination of a proper and an improper axis, depending upon the rules which have been laid out by the Euler's theorem. So, it has to be PII or P by I or whatever. So, those combinations therefore are allowed combinations to represent the cubic point group symmetry. So, this essentially now covers what we would like to have covered for the point group symmetries. The 32 point groups now are distributed to the 7 crystal systems, and the 7 crystal system characterization we have already analyzed with respect to their cell dimensions A, B, C, alpha, beta, gamma. They are identified with respect to the crystal system. Their corresponding lattice symmetries have also been identified. For example, there is always a primitive lattice that will be associated with triclinic and nothing else, With a monoclinic symmetry, we can have a primitive as well as the possibility of a C centered lattice. C could be either A or B depending upon the definition of the unique axis. If our unique axis is B, then it is always referred to the C centering of the lattice as the possible Bravais lattice. So, we therefore have the next slide shows us the possibilities of what kind of lattices which we can associate with each one of the 7 crystal systems. So, we have for example here triclinic. Triclinic is associated with the lattice symbol P, which is an accepted symbol, and then we have ABC not equal, alpha beta gamma not equal, that is the definition of the unit cell. And then the number of lattice points, we have 1 lattice point in the case of a primitive, and the point group symmetry. See, this is very interesting. We can have 2 associated symmetries with the point group. That means 2 point group symmetries, 1 and 1 bar are possible. But notice that the symmetry that is associated with the lattice is always 1 bar. So, if you just look at a triclinic lattice and you are given the information only about the triclinic acid lattice by some experimental procedure, it is always a 1 bar symmetry. That means the lattice associated with the triclinic system is 1 bar. On the other hand, the point group symmetries are 1 and 1 bar. So, this happens throughout in these cases. The highest symmetry associated with, you see here it is m is 2 by m, 2 by m, 2 by m, and as we go down, the highest point group symmetry is the symmetry of the lattice. So, the lattice symmetry always keeps the highest possible point group symmetry associated with the 7 crystal systems. So, individually we can have more than 1 point group symmetry associated with each crystal system. On the other hand, we can also have the types of lattices differ. So, here for example, in the case of a monoclinic system, it could be a primitive lattice or a C centered lattice. So, this is the definition for the unique axis being B. So, beta is always different than 90 degrees. The convention says that beta angle is preferably greater than 90 degrees. Modern day crystallographers, particularly people who just solve structures without thinking about what is going on, they even report beta angles less than 90, but crystallographic convention demands beta to be greater than 90. There are lots and lots of publications in literature, particularly by chemists practicing crystallography or somebody who takes crystallography for granted, or the mistake of the manufacturers and also the software people who have developed these packages. Beta is many times reported less than 90, but as a quality crystallography expert, one should always have beta greater than 90 degrees in a monoclinic representation. This is a must and people should take care of it. So, those structures in which beta is less than 90, there are certain things which they will be missing, particularly in terms of data completion and so on. This is something which we will discuss when we come to the experimental methods of structure determination. So, the number of lattice points associated with the primitive monoclinic is 1, and the number that is associated with the C centered lattice is 2. And this point group symmetry, as we saw, is the highest symmetry that can be associated with the monoclinic system, which is 2 divided by m. Then we go to the orthorhombic system. In case of the orthorhombic system, we have 4 possible lattices: the primitive lattice, the C centered lattice, which could also be represented as A and B, A centered as well as B centered, because A is equal to B is equal to C. Then we have the I centered lattice, which is the body centered lattice, and then the face centered lattice. Notice that the lattices are independent of the point group symmetries. So, the point group symmetry of the lattice is very high, whereas the lattice symbols will generate different types of lattices, that is number of lattice points. The number of lattice points associated will decide on the nature of the Bravais lattice, but the point group symmetry of the lattice is the highest point group symmetry associated with the crystal system. So, just by looking at the point group symmetry of the lattice, one should not conclude the point group symmetry associated with that particular crystal system. The crystal system still has 1 and 1 bar, for example, in case of the in case of the triclinic lattice. These are issues which one has to thoroughly remember and understand. In fact, understand it. Once you understand it, you will obviously remember it. It is not given in any textbooks. So, this is something which has to be learnt by practice, and at this time you are learning from this course. So, the 4 types of lattices that we can associate with an orthorhombic system, the P, C, I and F, will carry the number of lattice points like this: 1 for primitive, 2 for C, A or B, and 2 for the body centered, which is x corresponding to x, y, z, and half along x, half along y, half along z to be added to it. So, that means half, half, half is an additional lattice point along with the 0, 0, 0, which will generate 1/8 of the points around in the lattice. The F centered lattice will have 4, 1 corresponding to all the corners and 1 each for each of the faces A, B and C, which is centered. So, we then go to the tetragonal system. In the case of the tetragonal system, because A is equal to B, it is a square lattice, we cannot have any independent centering associated with it. Because of the fact that A equals B and not equal to C, we cannot have a face centered lattice, because the face centering will automatically move the A, B, C, because the translational periodicity is operational here, and therefore, we get only a primitive and an I centered lattice in case of the tetragonal system. We do not get any other type of lattices, and this therefore gives us the number of lattice points 1 and 2, and the maximum symmetry that is associated with the tetragonal symmetry is 4 by m, 2 by m, 2 by m, which is simplified and written as 4 by m, m, m. Obviously, we cannot have a combination of this kind. It has to be 4 by m, 2 by m, 2 by m, which will have both primitive and inversion associated with it. Then we have the cubic system. We have the case of the cubic system as P, I and F, and 1, 2 and 4, and you see the symmetry is the m3m, that is the highest symmetry one can have, 2 by m, 3 or 3 by m associated with it, and then the mirror symmetry. So, m3m is the highest cubic symmetry we can have. So, 3 and 3 bar are possibilities, but m3m is the symmetry that is associated with the lattice. Then we have the trigonal and the hexagonal system. As I mentioned, that the relationship between these two is very subtle and it can be converted. For example, if you see they are rhombohedral, there are 2 settings. One setting is actually the setting associated with the hexagonal system. A equals B not equal to C, alpha, beta, gamma. Alpha, beta are 90 degrees and gamma is 120 degrees. On the other hand, the hexagonal system is the primitive lattice, which is A not equal to B, A equals B not equal to C, alpha, beta 90 degrees, gamma is 120 degrees. You see in the rhombohedral setting we have A equals B equals C, alpha, beta, gamma are all equal, and they should be generally less than 120 degrees. And the highest point group symmetry that is associated with this is 3 bar m, and in this case it is 6 by m, 2 by m, 2 by m. So, this generally tells us how we now distribute the crystal systems, the Bravais lattices, the type of the lattice we define, that is the unit cell conventional unit cells, the number of lattice points, and the highest point group symmetry which is associated with the lattice. Of course, we can have one more column up here which will tell us all the point group symmetries which we can associate, but I think we have already seen the separate table for that. It is always good to have it in a separate table, which we have already seen several times. And therefore, this now generally tells us that in a crystal system, when compounds crystallize, we have a 3-dimensional crystal. The property of the 3-dimensional crystal we have seen so far is the periodicity that is associated with the crystal, the translational periodicity, which therefore invokes the presence of a unit cell. And there are several possible unit cells associated with each one of these crystal systems, which we have seen, and with them are associated the Bravais lattices. So, in order to actually represent an object inside this unit cell, we need to have all these satisfied. That means, let us say a molecule goes into one of these crystal systems. The molecule will now face the possibility of having any of these Bravais lattices. depending on any of these Bravais lattices, the number of lattice points will change. So, that means that the lattice that is associated with, let us say, the C centered lattice will have to have the same object also appearing with respect to the C centering. Here again, in the case of the F centered orthorhombic lattice, there must be 4 of those, and this is the way in which we have to associate the objects. And these objects, when once associated with the lattice points, now we will go to the corresponding point group identification. They will be already symmetry associated with the lattice. So, now the possibilities of the other independent space groups will come up, and depending on that the compound reorganizes itself. So, when a compound crystallizes in a 3-dimensional lattice of this particular kind, it faces all these restrictions, and because it faces all these restrictions, it is now possible to find out the position of the atom or the molecule or the association, the molecular assembly, whether it is a small atom or a big atom or a big molecule or a small molecule, it does not matter. Once we are in a crystal system, these are the rules which have to be followed without fail.